Can you please tell me if you can hear me? Okay, great. Today, first I will welcome everyone for the second lecture of CPHQ course. Today our speaker is Dr. Raya. She's basically from UAE, but unfortunately she won't be joining us live. But she had shared a lecture. This lecture will be recorded. If you have any questions, you can just write down in the chat box. I will try to forward to her or I will try to answer. So basically, her introduction, I will start with the introduction of Dr. Raya. She's working in Cleveland Clinic, Abu Dhabi, as a clinical staff pharmacist too. She has done master's in pharmacy. She is certified professional in healthcare quality, and she is also board certified pharmacotherapy specialist and critical care specialist. Along with that, she is doing master's in healthcare quality and safety from Howard University. So I will just play the recording. Please try to listen because one of the most important topic is the introduction to statistics. A lot of questions will come and they are easy to understand and easy to get score because they are very easy to understand and easy to answer also. So please let me know if you can hear the recording.
And welcome to this session on Introduction to Statistics. I hope you find this helpful for your CPHQ exam. My name is Raya. I'm a pharmacist at Cleveland Clinic, Abu Dhabi. And I truly apologize for not being able to be with you in a live session. Unfortunately, I had a last-minute conflict, but I trust that this lecture will still be helpful to you. And I'm sure your course directors will be able to direct you to the right people if you have any questions. And before we start, I just want to make sure everyone understands that this lecture, or perhaps any of the lectures presented, are not a replacement for your textbooks references. However, this is a review of what I expect the exam would ask you about, and I hope it helps guiding you. And I will also be sharing some questions that I recall from my exam, and I hope that also helps. So let's go ahead and get started. As a disclosure, I have no financial relationship to disclose, and I will not be discussing any off-label use or investigational drugs or any drugs at all in this lecture. So the learning objectives, at the completion of this activity, you will be able to understand and apply some basic principles of statistics, understand descriptive statistics, explain hypothesis testing, error types, confidence intervals. We'll go over research questions, hypothesis testing, data types, sampling design, bias and confounding, statistical tests, type 1 and type 2 errors, statistical significance, and some practice exam questions. So you need to start thinking about statistics as a whole story, as a research question. When you start thinking of a research question, you will formulate this into a hypothesis to test. You probably heard of the term null hypothesis. It is when you restate your research hypothesis to one that proposes no difference between the groups being compared. For example, let's say you want to look at the risk of developing peptic ulcer in people who drink tap water. So your research question would be, does drinking tap water increase the risk of developing peptic ulcer? That's your research question. Now, the null hypothesis would be people who drink tap water have the same risk of developing peptic ulcer disease as those who drink bottled water. This is how you formulate, how you transform your research question into the null hypothesis. The alternate hypothesis is what you're trying to prove. You are trying to prove that people who drink tap water have a greater risk of developing peptic ulcer compared to those who don't. But the alternative hypothesis cannot be tested directly. This is why we come up with the null hypothesis. So your alternate hypothesis would be people who drink tap water have a greater risk of developing peptic ulcer. Now, if you think of this as an analogy to the courtroom, for example, your suspect is innocent until proven guilty, meaning that at the beginning of the research, we believe that the null hypothesis is true, that people who drink tap water have the same risk, and we are trying to prove it wrong. And that is your research hypothesis. Now, when you start a research, you want to study a sample. And there are techniques for sampling, and there are types of sampling that we're going to go over. So, and again, I want to remind you that I won't be going in depth into any of those topics. This is just an overview of the things that I remember I was asked on in the exam and the things I think you should know. But you should always go back to your references. So say we want to find out what the average age of the population of the UAE is. Now, ideally, we have 9.9 million people in the UAE currently, and that is at least the latest statistics I know of. So ideally, you want to sum the age of all 9.9 million people and divide that by the number of people to get the average age of the population. But that is not practical and almost impossible. So what you do instead is you formulate a sample of your population. Now, the population is the total people, total number of people or total number of subjects you're thinking of. Your sample is a portion of that population that you want to study. You would take different samples from different regions, say 100 people from each emirate, or because, for example, Abu Dhabi is most of the UAE, you want to take like different samples from different regions of Abu Dhabi and the other emirates, and you will average the age of that sample. Say you have 1,000 people, you're gonna sum the age of 1,000 people and divide that by the number of those people, and that is your mean or average age of the population. Now, when it comes to sampling, and sampling is very important, and we'll look at possibly reasons why the right sampling technique is very important. There are different types of sampling. The two major categories are probability sampling and non-probability sampling. Probability sampling is a technique in which the subjects of the population have an equal opportunity of being selected into your sample. The non-probability sampling is a method of sampling wherein it is not known that which individual from the population will be selected as a sample. This means that they probably don't have an equal opportunity of being selected into your sample. And there are the non-probability sampling introduces problems like bias and confounding, which affects your statistical analysis and the significance of the results you will come up with. And we will discuss this later. So what are probability sampling techniques? You have the simple random sampling, which may be the most common and the least biased. Just like the example we discussed previously, you select a random sample of 1,000 people from the UAE, for 100 people from different regions to average out their age. That's totally random. There is no criteria that you're selecting, except that those people reside in the UAE. Systematic sampling, it's when you want to select, for example, you want to look at turnaround time for blood tests. So you go ahead and select every third sample of that day. The reason for that is to be systematic, is to be random, and is because you have a limited number of samples and you want to select the most representative sample. Stratified random sampling is another type of probability sampling. In this form, you are looking at one big question in two strata. For example, you want to find the average age of the UAE population in men versus women. So you have two strata. You have a strata of men where you randomly select from your population. You randomly select the men from your population and put them in one strata, and then you randomly select the women one in your population and put them in another strata. This is because you want to look at two sides of your research question. Cluster sampling is similar to stratified sampling, but in this case, you want to, for example, look at the average of the population of each region separately. So you have each 10 people in one cluster. You divide your 1,000 people into clusters of 100, and you pick random people from those 100 into one final sample. And all of those are used because of the specific, the way of sampling depends on what kind of outcome you are looking for and what kind of sample you're beginning with and what kind of research question you're addressing. The non-probability samples, and again, those introduce biases. First, you have the convenience sampling, and from the name of it, it is the sample that you select because it's conveniently available. Let's think of a college student who wants to, again, look at the average age of people, of students in their college. Say this is a pharmacist and wants to know the average age of students. This is not the best example, but just to make this more clear. So it's a pharmacist and wants to look at the average age of students in pharmacy school. So they take different people from their batch, for example. Now, and they do that during their time in college, maybe after a class or before a class. So it's a convenient sample because they are selecting people around them, and because it is bound to a specific time frame. It's not representative of the population. It can give you insight into your research question and outcomes, but one of its problems is that it's not a representative sample. However, it might be the only sampling technique you can afford due to time constraints, budget constraints. A lot of the sampling techniques are actually based on cost as well. The snowball sampling, that same student is collecting that information through a survey. So they hand out the survey to two of their friends and ask their friends to pass this out to more people, and those friends to further more people. So this is a snowball effect where your sample increases through distribution, through your own sample. The quota sampling is when you have specific criteria to look at. So you want to look at the average weight in the UAE population, but you're only looking at males above 50. So you have the males above 50 sample in your population, and then you furthermore randomly select from those. And the judgment sampling is the last type. Some books refer to judgment sampling or expert sampling. Some references refer to those as two different things, but they are really the same type of sampling. The judgment sampling is when you use your expertise and knowledge to decide which sample is best for your research question. You want to look at the turnaround time again for your lab samples, your vancomycin results, for example, because you think that the turnaround time is too long and you want to improve that. So you know that the lab functions differently in the evening time and on weekends. So you avoid those times, for example. You decide to select samples only from your 8 to 5 day. And then you have 200 samples per day, which is too expensive to analyze or to look at. So you decide that only 10 samples a day are enough. It's because you are the lab technician and because you know the circumstances well. Your judgment and your expertise is to decide which type and time frame of samples is suitable for your research question. Now we mentioned bias several times, and I'm not going to go again into the details. Please always go back to your textbooks and references. But generally, bias is a systematic error. It's not intentional, and it causes deviation of results from the actual value. There are different types of bias. Selection bias, like those presented, depending on your sampling design. Recall bias, when you ask a customer about their experience, they are more likely, for example, to remember negative experiences compared to their positive experiences. So that's recall bias. Publication confirmation bias. If you are doing a systematic review article, the literature is more likely, or publishers are more likely to publish positive results and hide away the negative results. So those are all types of biases that at the end present you with an outcome that is not representative of the actual truth in the universe. And if you go to any of the references, there are multiple types and multiple examples that will help you better understand. But really, for the purpose of the CPHQ exam, you won't be asked on the type of biases. At least this is what I remember from my exam and what I think is fair. But you are expected to understand what bias means and what kind of sampling techniques may introduce bias. Confounding is a form of bias as well. It's when you have a research question or an outcome that is affected by multiple other variables. For example, you want to study the effect of exercise on weight. But exercise is not the only thing that affects weight. There are also other reasons, age, comorbidities, lifestyle, exercise habits. So you want to factor in all of those, because otherwise, if you don't, then your outcome is confounded, is contaminated by not factoring in those other factors. And this is when multiple regression analysis comes to play, and that we will look at a bit closer in the following slides. So now you have your research question, you have your hypothesis, you have your population, you are going to collect some data, and you want to know, you want to be mindful of your data types, because later on you're going to have to decide which statistical tests you should apply. Data can be categorical, that is your nominal and your ordinal data. Nominal data is any question that has only two answer possibilities. Do you smoke? Yes or no. Gender, male, female, anything that only has two possibilities. Ordinal data is characteristics in categories and are ranked, ordered. When you do a survey and they ask you how strongly do you agree with something, and you have a scale of 1 to 5, that is ordinal data. Continuous data are the easiest to deal with, are the easiest to handle, and I would think most data is continuous data. And there are even ways, if you are interested in deeper statistical understanding, there are ways to transform your non-continuous or your categorical data into continuous data. And I remember an example. So I did a study for my master's a couple of months ago, looking at when, at an intervention, and whether or not it affected the time I came to work in the morning. So instead of looking at the data, for example, as did I show up on time, yes or no, I could look at the number of minutes before or after the punch-in time. And this is one way I transferred my categorical yes or no data to continuous data. So anyway, continuous data could be either an interval, which is the distance between each point, and it is equal between the two consecutive points, and there is no true zero, like Celsius or Fahrenheit. Maybe actually Fahrenheit as a better example. And the ratio is the distance between each point is equal, but there is a true zero, like height and weight. No one's height is in the minus, right? Or weight. Now, after collecting your data, you want to understand their spread, their mean, the standard deviation. All of those help you understand the variability of the data. Central tendency, multiple tests compare means, for example. So what is central tendency? It can be the mean, the median, the mode. The mean, as we've seen in a previous example, is a sum of all values divided by the total number of values, and it's the most commonly used variable or parameter of central tendency. The median, if you have a random number of numbers from 1 to 30, you want to arrange those in a descending or ascending order, and then you want to pick the middle number. The mode is the most frequently repeated value. So that same example, if you have a number of numbers between 1 and 30 and say number 16 is there 3 times, and that this is your mode. But it is less representative of the central tendency because one set of data can have multiple modes. The differences here that you need to know is that the mean is affected by the outliers. For example, if everyone's age falls between, say, I don't know, 1 year to 50 years, and then your mean is 25, but then you have one person's age who is way like 60 years, for example, so that person's age would affect your mean. The median and the mode, however, are not affected by outliers. So sometimes, depending on what you're looking for to represent, you want to look, and whether you are concerned about outliers, your choice of central tendency would differ. But the mean still is the most frequently used. The measures of variability, I mean, there are different applications for that. The range is the difference between the highest and lowest values. Sometimes you really want to just understand the spread of your data. The average population age in the UAE. So you want to see the spread of that age. What's the highest portion? What's the lowest portion? The interquartile range is the range of the middle half of a distribution. So if you look here, the interquartile range is usually in this area, but most of your data is in the intermediate range. So this is all just understanding. It doesn't really apply to any statistical test. It's only understanding the distribution or the dispersion of your data. Standard deviation, however, is an important parameter. It's the average distance from the mean. It's a complicated formula that you don't need to understand, or at least to memorize for the, you definitely need to understand, but you don't have to memorize for the purposes of the exam. But the variables here are different calculations that any statistical software would calculate automatically for you, but it's always good to understand the origin of these calculations. So the standard deviation also explains, just thinking of how to best word this, explains the probability density. So for example, and you can hear multiple different terms for the standard deviation depending on what type of research question you're looking at. If you're looking at a research question, it's the SD, or the standard deviation. If you're looking at multiple means of the population, then it's mu. If you're thinking of statistical process control and improvement projects, you're going to use sigma. But they're all the same concept. At 3 standard deviations, what this information tells you, I mean, whatever this value is and this value is, we're going to just use the 3 standard deviations. This means if you repeat this study again with the same population, similar population, similar size, similar circumstances, you are 99.73% or the probability is that your data will 99.739% fall within this range. If you're looking at 2 standard deviations, it's 95% possible that it will be in this range, and most of your data will be in this range. So the standard deviation is the difference from the mean, and is also the probability of your 1 point being located within this range. So your data type decides as well the statistical tests that you need to use, and of course the outcome you're looking for. Parametric tests are based on an assumption about the distribution of the underlying population from which the sample was taken. It sounds complicated, but it really isn't. It just looks at the data that is normally distributed, which is the bell shape that you saw in the previous slide. So the most common parametric assumption is that the data are approximately normally distributed. The t-test is one of the most common ones, or the student t-test. It usually assesses whether the means of two groups, and I emphasize that you should remember this. It compares two groups only, because if it's more than two groups, it's a different test. And those are the types of questions that you will be asked about. And I'll show you one of those, but the trick is always here. They'll ask you if you have normally distributed or continuous data, and you're comparing this treatment to this treatment, excuse me, which test should you be using? So it assesses whether the means of two groups are statistically different from each other. Regression analysis, which is the correlation, and I emphasize it's the correlation, not the causation. That's another trick that you might see in the exam. So you have two variables, and you want to see how well they correlate to one another. One example I remember is, for example, the dose of Levodox or enoxaparin and the level of factor 10 in the blood. So that's one example of correlation. This is not caused by that, but is correlated to it. The R can range between -1 to 1. -1 means an inverse relationship, but it's a perfectly inverse relationship. 1 is a perfectly positive relationship, which means as this variable goes, this variable goes the exact same amount. And 0 means no relationship. So you always want your R to be closer to 1 or -1. Multiple regression analysis estimates the effects of two or more independent variables on an independent measure. So the weight example we talked about earlier. You want to study the effect of exercise on weight, but you have to think of the age, the comorbidities, the lifestyle, the length of the exercise, the type of exercise. All of those are important to analyze your outcome. So when you have multiple factors affecting your outcome, this is when you want multiple regression analysis. And all of those complicated tests are done by softwares. So for the purpose of the exam, you are not required to be able to do these tests, but you are required definitely to understand what these tests look at and when to use them. And again, I'll be repeating the same sentence all over this lecture. You always have to go back to your excuse me, textbooks references. And I'll tell you at the end of this which books that I found the most helpful. For non-parametric tests, it is a class of statistical procedures that do not rely on the assumption about the shape or form of the test, of the distribution from which the data were drawn. So whether this is normal or not normal, it doesn't affect the test selection, but it mostly assumes non-normal distribution. Chi-square and categorical data. The chi-square measures the statistical significance of a difference in proportions and the most commonly reported test in medical literature. It is for the non-parametric tests. Usually the chi-square is used to compare what you expected, the outcome you expected versus the outcome you actually have, based on your hypothesis. Now, there are multiple systematic errors that you might come across when you reach to your conclusion. Say you did your hypothesis, you practiced your research question, you have your sample, you did the statistical tests, now you reach to a conclusion. How correct is this conclusion? It also, of course, it depends on how well you designed your research and whether or not you used the right tests, but there are some things that you cannot entirely eliminate, but you can minimize. So if an investigator may always reach a wrong conclusion, and those we refer to as type 1 and type 2 errors. So type 1 error, which is a false positive, it occurs if you reject the null hypothesis in your population, in your research population, when it is actually true in the true population. So let's go back to the example. So in your research question, or your null hypothesis, is that people who drink tap water have the same risk of developing peptic ulcer disease as those who drink bottled water or who do not drink tap water. This is your null hypothesis. So your type 1 error is if you actually come to a conclusion that the risk is greater in people who drink tap water, when actually it's not. So you have rejected the null hypothesis that is actually true. And this is a systematic error that happens by chance alone. It's not, sometimes it's not because, or not sometimes, I mean, type 1 error happens despite the fact that you actually did everything right. It's just by chance alone that your sample was not representative, and the results in the sample do not reflect reality in the population. Meaning that if someone else does the exact same research, they also randomly sample people who drink tap water and compare them to people who don't and who drink bottled water, they may reach to a different conclusion. Not because your research was wrong, it's because you were unlucky and you had that error by chance and your sample was not representative. Type 2 error is a false negative, occurs when you fail to reject the null hypothesis that is actually false in the population. So for example, you come to the conclusion that there is no risk in increasing peptic ulcer and that the risk is the same between people who drink tap water and people who drink bottled water. But in reality, there is actually an increased risk. So they can never be avoided. Type 1 and type 2 errors can never be avoided entirely, but they can be minimized. So if you increase your sample size, you minimize the likelihood of a type 1 error, because the larger the sample, the more randomized the sample is, the more it resembles your population. There are other things that you can do to the design of your sample or your research, but you always have to bear in mind the cost, because increasing the sample size comes with a specific cost, and again, those are better explained in your books and references. So alpha, now we understand the type 1 and type 2 error. We want to see how these look like in statistics, right? So alpha is one type of statistical significance estimate. The investigator establishes the maximum chance that he or she will tolerate of making type 1 and type 2 errors in advance of the study. For example, before we get to that, the maximum probability of committing a type 1 error, which is rejecting the null hypothesis when it is actually true, is called alpha, or the level of statistical significance. Let's look at, for example, the study of the effect of exercise on fasting blood glucose levels. And let's say that this study is designed with an alpha of 0.05 or 5%. This means that we have set 5% as the maximum chance we will accept to make a type 1 error, to incorrectly reject the null hypothesis if it is true, and thus say that exercise and fasting blood glucose levels are associated in the population, which in fact they are not. So I am fine if 5% of the time I come to the wrong conclusion, and it's an acceptable, and most studies are set of an alpha of 5%. This level is of reasonable doubt, And this is what the investigator will accept and will use statistical tests to analyze the data after the study is completed. Now, power is the probability of making, not power, beta is the probability of making type 2 error, which is failing to reject the null hypothesis when it is actually false, finding that there is no risk when there actually is. And beta, and this term is called beta. Now, the power of your study is 1 minus beta. It is the probability of correctly rejecting the null hypothesis in the sample if the actual effect in the population is equal to or greater than the specified effect size. You want to be, in other words, you want to be sure 90% of the time that you have come to the right conclusion. Now, what does that mean? If beta is set at 0.1 or 10%, the investigator has decided that she is willing to accept a 10% chance of missing the association of the specified effect size if it exists. There's a 90% chance of finding that association of that size or greater. So back to the example, the study of the effects of exercise on fasting blood glucose level with an alpha of 0.05 and a beta of 0.1 means in 9 of 10 similar studies, the investigator would correctly reject the null hypothesis at the specified level of 0.05 and conclude that exercise is associated with fasting glucose levels. This does not mean that the investigator would not be able to detect a smaller effect of the population. Let's say the initial effect we were looking for is 20 milligrams per deciliter reduction. If you set your alpha to 0.05 and beta to 0.1, 90% of the time you will reach to the conclusion that that exercise reduces glucose levels by 20 milligrams per deciliter. Now, that 1% or that one study or that 10% may find the reduction of 15 milligrams per deciliter reduction, which is not wrong, except it's not what you want. So that one study is not wrong. It just does not give you the same level of significance or the same size of the effect that you're looking for. Ideally, you want alpha and beta to be as close as possible to 0, minimizing the possibility of false positive and false negative, but you want those balanced as well. So if you set alpha at too high, now generally, and those are arbitrary numbers, but most studies do set alpha or the p-value to be less than 0.05, or they accept a 5% chance of error by chance. If you set this at 99%, this might sound appealing because you will be correct 99% of the time, but this also means that there is still that you will be missing out on that conclusion because you set your chance to only 1%. So this increases your error rate on the other side. So this means instead of like 5% chance of error, it's 1% chance of error, but there is still that 4% chance of concluding the opposite, which is also wrong. I don't know if that makes sense. But you want that number to be balanced. You don't want to be too strict with your criteria that you would create other problems. Ideally, to minimize the chance of these errors as much as possible, you want to increase the power of your study. Your first method is to increase your sample size, but that always comes with a cost, so you don't want to exhaust your budget as well. So you want to be very careful with your techniques. Sample size planning aims at choosing a sufficient number of subjects to keep the alpha and beta at an acceptably low level without making the study unnecessarily expensive or difficult. And as I said, a power of 80% or 90% and an alpha of 5% is usually what most studies in the literature go by. Now, we understand what alpha is. We want to understand what it looks like in statistics. So after analyzing your null hypothesis, you use your statistical tests to reach out to the p-value. The p-value is what you compare to your alpha. So it's the probability of seeing by chance alone an effect as big as or bigger than that seen in the study if the null hypothesis is actually true. So in your glucose study, you set your minimum goal to see a 20 milligram per deciliter drop in your glucose level with exercise. That's your p-value. So you would of course be happy with any result that is also over 20. So 20 milligram per deciliter reduction is good, 25 is good, 30 is good. All of those are achieving your outcome. If that chance is small, then the null hypothesis of no difference can be rejected in favor of its alternative, and that there is a difference. By small, we mean a p-value that is less than alpha, the predetermined level of statistical significance. Now, a non-significant result, like p-value greater than 0.05 or greater than your alpha, does not mean that there is no relation, no correlation. It only means that it is not the effect size that you were hoping for. So, and again, in clinical terms, even a negative or a non-significant result is still a result. Confidence intervals are also another way of analyzing your results. It is the mean of your estimate plus minus the variation in that estimate. So it's the range of values that you want your outcome to fall in between to consider that significant, and you would use that for comparing groups. Confidence is just another way to describe probability. If you set your confidence level at 95%, then with your outcomes, you are confident that 95%, 95 out of 100 times you repeat your study, you're confident that the estimate will fall between your upper and lower values. And the confidence level is 1 minus your alpha. So if you set your alpha to be 0.05, which means 5% of the time you accept that you might reach to the wrong conclusion by chance, then 95% of the time you are also confident that you reach to the correct conclusion by chance as well. If your alpha is 0.05, then your confidence interval is the 95% confidence interval. Now let's review some research, some practice questions. And here I'm not shy to go back to my notes because I don't only want to show you the correct answer, but we also want to understand why the other answers may be wrong. So, a healthcare quality professional wants to measure the success of a corrective action plan with a 95% confidence interval level. The average daily census at the Quality Professionals Organization is 1,000 patients. What's your best sampling technique for this study? To review your sample, would you look at 10% of all discharge records for the past quarter, or would you look at all the active records on one day in your past month? Or would you select randomly 30% of the records based on preliminary review, or would that be the number of records needed using a statistical method? Now, if this were a live session, this would have been more interactive. I apologize again, but nonetheless, we can still go over the necessary information. So the right answer here is D. It's the number of records needed using a statistical method. You're going to apply a statistical test to decide which sample size would be appropriate. Now, 10% of all discharge records, this is not a representative sample. All active records on one day in 1 month is also not a representative sample. 30% of records, that's also, choosing all of those numbers randomly does not really make sense and will probably not provide you with a representative sample. So you want to really use the appropriate statistical method to calculate the number of records that you may need. And all of the questions I'm sharing here are questions that I actually had in actual CPHQ exam. So if you feel that those are non-relevant, this is why I'm telling you that your main reference should be your textbooks. Question number 2, the Utilization Management Committee is reviewing length of stay data for a particular procedure. In comparing data by physician, which of the following statistics would be most helpful? Are you going to look at the correlation, the range, the mode, the mean? So let's think a little bit about this. Correlation is used to describe the relationship between two variables. The range is the distribution of the variables. The mode is the most frequently repeated value. The mean is the average that you would use to understand the difference between two sets of your data. So here you would want to use the mean because the other tests are not applicable in this case. Question 3. Which of the following sample techniques selects participants based on their availability in a certain place during a specific time? And I hope this will come to you directly because this is the convenience sample. And if you are not sure why, please go back to the slides where we discussed the sampling designs. Question 4. What do we use a t-test for? Would you use it to display the size of a sampling variation? Is the t-test really a way to explain variation? Are you going to use it to evaluate the effects of two different treatments? I like that because this is what a t-test would be used for. Are you going to evaluate the differences among 3 or more treatments? Remember when I told you the trick questions? So 3 or more is not a t-test. Display a listing of the number of occurrences of a variable. That to me sounds like the mode. So your correct answer would be B. Question number 5. Facility A is investigating its medication administration time for a specific diagnosis. Evidence-based guidelines indicate that administration of a particular drug within 30 minutes significantly improves patient outcomes. Your national average, your benchmark is 32, but your friend facility is doing well at 28, and you are a little bit above at 35. What are you going to do? Are you going to determine whether its rate is within one standard deviation of the national average? Maybe, but maybe not the first thing I would think of. I would decrease the rate to meet the national average. That's what I want to do. So this is the outcome. This is not the method. Contact facility B to determine its practices. I like that because you want to know what's working and maybe you can apply the same. Identify the average time of its competitors, maybe, but not at this point. So the right answer would be C, because you want to know what's working for other facilities before you start looking at what works, what you can apply here, or start looking at other competitors. And now I know this is an unusual way of displaying references, but I feel this is what might help you more. So the references I used here and for my preparation for the exam, the HQ Solutions, it's a wonderful resource. It's 100 pages. No, actually a couple of 100 pages. I was over this book in 3 weeks. It's a simple language, really easy to follow, and it covers absolutely everything you need to know for the exam. Designing clinical research, I found this very helpful with the research design and the study designs, and I think it's also helpful. And I did buy the practice test exam. It's $185. What I would recommend, since you're a group of participants, you may share the cost and gain access, share the username and password. I don't see anything wrong with that. And you have access to this for a year. So from the time you actually start the test, and it gives you the correct answers. So I really think this is what helped me the most pass the exam. So with that, I will end my presentation. Thank you very much for attending, and I wish you luck with your exam. I'm sure your course directors will be happy to assist you with any questions or refer you to the right person, and good luck.